our production actually just is the connectors. So most of the parts were the design of the part will go through the injection molding simulation. And that's why we receive a lot of requests for injection molding simulation. So I'll go directly to the stress analysis introduction. Okay, you can see there are two pictures here. From left, it's under the stress tab. This is the Moldex3D stress analysis interface. So under the stress tab, there are two types of analysis. One is stress. So this can enable to perform the linear elastic stress analysis before or after injection molding analysis, even you don't have the FEA software. So you can define the boundary conditions, the force boundary condition, the pressure, or the displacement. And also, if you run the injection molding simulation, you can include the flow-induced residual stress. Also, if you have the data for Wetland factor, you can apply it here. It gives you some options to do the stress analysis. I think this is convenient to use. And if there is a temperature effect, you can go to the annealing, this type of analysis. So it can simulate the annealing process to observe the stress relaxation on the different temperature variations. So you can define the temperature profile from room temperature to high temperature, but you cannot go below the cannot go to the negative. And also you can do the stress analysis, which means you don't consider the viscoelasticity. So you uncheck this, or you can when you check it, it will be the linear analysis that's consider the viscoelasticity. So, but using this function will need an extra license for the stress. So here, this is a model, a viscoelasticity model in Moldex3D. I want to talk about it a little bit because it's useful for it's critical for the annealing. So there are two. It includes the two model. One is a WLF equation. That's a short of William Landau-Ferry equation. That's a experimental, empirical equation that considers time and temperature superposition. So in short, that means so when you do the relaxation, you can finish the relaxation at room temperature like in 1 day. Then instead you can put the part in the oven at high temperature. Maybe that relaxation only takes 1 hour. So longer time or higher temperature can have the same effect. And generalize the Maxwell model. That's a most general form for linear model of viscoelasticity. So it's just a combination of the spring and the slides in parallel way. So, but usually most of the data has only the generic data for these parameters. So if you want to add more accurate data, you need to do some test. And stress analysis using general purpose CA software. I see this afternoon one gentleman asked a question about how to get the mesh for FEA analysis. I think this is the answer. So go through the FEA interface. You can choose different solvers and write the file for this solver. And so you can use the original mesh using the deformed mesh or the mesh or some mesh coarse mesh you did yourself. It's called a mapped mesh. And also, I think this is it has a material property definition. I think that's very helpful for the fiber reinforced polymers. So you can help define the elasticity and the coefficient of some expansion. Of course, they are anisotropic because it will depend on the fiber orientation calculated in the injection molding simulation. Also, the elements are grouped by the fiber orientation. So you don't it's not the element has the same a similar fiber orientation where have a group. So you will it will help you a lot when you do run the analysis. When the you have millions of mesh, you don't have to define the material property at each element. Also, it can help to export the fiber orientation, laser stress, and the temperature history. So you can play around this by if you can code by yourself or define the material property yourself. So here I'm going to talk about the application. It's a practice for in-house. So we have a study part, so that you can see here it has its cracks. But we did this part through has a cracks after the thermal shock test. Before it's okay, and we did the injection molding simulation, and we didn't. But we don't do the stress analysis, so we didn't catch it before. And the interesting thing is there are many features like this in this part. Only this one has cracks, and the material is a PBT plus 30% glass fiber. So we need the first thing we need to do. We did is just go back and check the injection molding simulation and see if we can find some clues or signs that can help us understand it. In design, I think it's easy to solve this issue, but the question is we cannot catch it because we don't have some simulation result to show it. So when I checked, this is a part I used. This is features in the crack area, and actually these are symmetric. This part is symmetric. So there's the exact same one this end, but actually this one is good, but this one has cracks. So we check the flow from progression. It looks good to me, and also the weld line is not in the crack area. So and the warpage analysis, it has a residual stress also, but we didn't see the strange stress in this area. It has some stress concentration, but it doesn't stand out from the other areas. So the conclusion would be that the part doesn't has defect after molding, and I think that's why we have a good part after molding. But through the thermal shock test, the part cracks. So we see maybe the temperature will be a driving force, and considering this is a fiber reinforced polymer, so I want to check the stress, the fiber orientation in the crack area. So there is some difference, but not that obvious. So we need to find a way to show, and at that time I'm thinking maybe do a simple stress analysis will be a good idea. Just want to see when temperature changes, how much difference, what does it look like in the stress level. And unfortunately we have the Abacus license, so I just did a very simple geometry using the FEA interface to export the mesh and the material data. What I need to do just assign the mesh temperature from room temperature to 125 degrees C, then go back to room temperature, because this is elasticity. So initial stress and the final stress will be zero, because it's only the status dependent. But when I check the stress level at the high temperature, we can see that it's a big, very obvious difference that this area is a crack area, and it shows a strong stress concentration. But on the other end, this area, which is the same feature, but the stress level is much lower. So that's a good sign that we can find the difference even in the from the design. Using this, I think we can find it from the design stage. But that's where doing the FEA analysis takes extra work. Our main work can finish by Moldex3D. So when I know the Moldex3D has a stress analysis, so I started to try it. So I only need one more step besides the regular injection molding simulation. So I need to I choose the annealing analysis. The first one I didn't use the viscoelasticity, so just want to duplicate what Abacus did. So even this, so because it's elasticity, so even I set the profile the same as the actual, but it will be similar, the same as the setting in Abacus. Room temperature from room temperature and to 125, then go back to room temperature. And the initial stress and the final stress shows the same. Here there's some stress level stress here because this is the residual stress after injection molding. That's Moldex3D considers the residual stress automatically. But when I go check the stress at the temperature 125 degrees C, I also see an obvious change in this crack area. See this difference? So it's also a good indicator that this one will be a problem for us. Besides the stress analysis, I also the linear without the viscoelasticity. I also check try to use the viscoelasticity. And now this profile is matters. So because viscoelasticity, so it's time dependent. So actually at the end, the maximum stress happens at the end of the analysis at this point, and you will also see a very bad stress concentration. But this end doesn't have it. So I think this is also a good indicator. So now we have the multiple ways to predict this crack issue. So after now we did some modification to the features, just getting rid of this rib, and it tried to it will change the fiber orientation, and from this flow from it doesn't change much. It runs very smoothly. And after the stress analysis, we also didn't find the weird stress area. The first one is the result from stress analysis without viscoelasticity. This one is with the result with the viscoelasticity, and we don't see much stress concentration. So we think this will be a good. This geometry change will be good and can solve this issue, and that's what we did actually. And we in actual part we didn't see the cracks eventually. So this is a good example of how do we use the Moldex3D stress analysis. Besides this, we also have another example that's for the warpage analysis after annealing. We have the part. This is I cannot show all the part is just a wall. From the bottom is almost the same level. The geometry before and after annealing, but it's the top after annealing. This part leaning to the left. But after when I did did the stress analysis, we think it may have some difference, but actually both the stress with or without viscoelasticity doesn't show much difference. So this is before annealing. This is after. They are almost the same. So we talk to Moldex3D and actually find that the material data here. This is in 125 degrees C. The master curve. The modules changes. The curve of modules changing versus the time. You can see in the within the time I set, the modules doesn't change much. Usually there was a jump, like this obvious jump, but there's no jump here. I think that's the reason why it doesn't have a big change in the shape. So we probably we need to do a test about it, because this material data is generic, not so probably need more. It needs a test for accuracy. So I think this can give us a idea that maybe the material property also is critical for the warpage analysis or or the annealing analysis. So takeaways is that Moldex3D has a capability to do the stress analysis after molding analysis. Also, the material property is critical for analysis with viscoelasticity.